Okay, folks, today we're going to do a little bit of ACT review in preparation for the junior ACT test that is coming up. Most of the questions that are on the math portion of the ACT come from things that you've already learned in Algebra 1 and geometry. It's just been a year or two, and so it's nice to kind of brush up on that so that we can try to get you the best score that you possibly can get on this ACT. So today we're going to dedicate to just doing a very brief review of some basic geometry material that you might see show up on the ACT. And the first thing that we're going to look at is we're going to look at something called all the angles that are formed from when you have a set of parallel lines that have a transversal that run through it. So if you look at this picture off to the right, you can see we have a pair of parallel lines, lines M and then here we have line T. This is known as a transversal, and it runs through the two parallel lines, and it creates 4 angles here as well as 4 angles here. Now there's all kinds of angles and names for these angles, and I don't believe that you guys necessarily have to know the names of these angles. You really just need to know the relationship between these angles. So I first want to talk about 4 different types of angles that are formed that are congruent angles when you have a transversal running through 2 parallel lines. Now the word congruent just means equal. So we're talking about what are different angles that are formed, these 8 angles that are show you sets of equal angles here. Okay, so the first one I want to look at is called corresponding angles. Okay, and there's 4 sets of corresponding angles in this picture. I'm going to highlight one of them right now. Angle 1 and angle 5 would be one example of corresponding angles. You can see they're kind of both in the same position. We have angle 1's in the upper left, and then down here in this set, same thing, angle 5. Those 2 angle measurements are exactly congruent to each other. Okay, you can kind of see that there's some other ones here. For example, angle 3 being in the bottom left there, that would be congruent to angle 7. So we're just going to kind of jot down, these are called corresponding angles. They would have equal angle measurements with one another. You can see angle 2 and 6 would be another set, so we'll jot that down, angle 2, angle 6. And the last one would be angle 4 and angle 8. Okay, those are called corresponding angles. They're equal to each other. Another set of angles that are equal to each other are called vertical angles. An example of a set of vertical angles might be angle 3 and angle 2. Okay, you'll notice that what they have in common is they share the same vertex. Kind of feels like they're maybe kind of opposite one another a little bit there. Angles 3 and angle 2 are vertical angles, so are angle 1 and angle 4. So we could jot that down as just another example of vertical angles. Vertical angles, those are always equal to each other. If you were to move down in the second picture, angle 5 and 8 are vertical angles, and the last set would be angle 6 and angle 7. Those are vertical angles. Okay, let's move on to what are called alternate exterior angles. I want you to notice these 2 words, alternate and exterior. Okay, get the word exterior from the fact that if we're talking about these 2 parallel lines, angles that lie on the exterior, on the outside of the 2 parallel lines would be angle 1 and 2 and angle 7 and 8. These 4 angles are on the exterior. Now this other word here is alternate. Okay, alternate means we're on alternating sides of the transversal. So what would be an example of alternate exterior angles? Excuse me, that would be angle 1 and angle 8. You can see they're in the exterior, but they're on alternate sides. So let's write that down. Angle 1 and angle 8. The other set of alternate exterior angles would be angle 2 and angle 7. Okay, those are the only alternate exterior. Okay, and finally, we are talking about alternate interior angles. So now we're talking about the angles here in the interior of the 2 parallel lines. But once again, the word alternate means they have to be on alternate sides. Okay, alternate sides. So that would be like angle 3 and angle 6. Those would be alternate interior. Okay, and the other set would be angle 4 and angle 5. Okay. Once again, I don't believe that you need to know the names of these, but you need to understand all these different sets of angles here, they're all equal to one another. Okay. If we were to look at the same picture, there are also various angles formed where the 2 angles are not equal to each other, but they are supplementary to each other. That means they add up to 180 degrees. Okay. So for example, a linear pair, and you should be quite familiar with this, a linear pair of angles just means 2 angles that form a straight line. Okay, 2 angles that form a straight line. So right here, angle 1 and angle 2, that would be a linear pair. You can see lots of linear pairs. I don't think we're going to write them all down, but obviously angle 3 and angle 4 would be another linear pair. Even if you turned and looked at it this way, angle 3 and angle 1 That would be an example of a linear pair. We'll do one more from this top set of angles, angle 2 and angle 4. Okay, that's another set of linear pair. And we could go around and do the same thing with these down here, but I think we get the idea there. Okay, let's take a look at same side exterior. Okay, so this is the same thing. We're talking about exterior, so we're only talking about the angles 1 and 2 or 7 and 8, but now we're saying same side. So that would be like same side would maybe be angle 2 and angle 8. You can see they're on the same side as the transversal, but they're in the exterior. Okay, what angle 2 and angle 8, you can tell by looking at the picture, they don't look like they're congruent. No, they're not. They're actually supplementary. Those two angles add up to 180 degrees. Another example would be angle 1 and angle 7. Okay, the last set of angles that we're going to discuss here in this picture are going to be same side interior. Okay, so now we're talking about they're going to be on the interior, but they need to be on the same side. So that would be angle 4 and angle 6, or angle 3 and angle 5. Okay, so these are supplementary. These ones up here are congruent. I think that you're going to be given some practice problems here, and knowing these relationships and how these angles kind of form will be helpful in doing some of those. Okay, let's just do a little bit more review here with some basic, this is just basic geometry here. Triangles, we want to make sure that we remember that in triangles, all the angles always add up to 180 degrees. I want to specifically look at what an isosceles triangle is with you here real quick. An isosceles triangle is a triangle that has at least two sides that are equal. So in this picture right here, this is an example of an isosceles triangle right here. And you can see that if I should have put tick marks here on this for you, denoting that these two sides are actually the same length. Okay. Now, one thing that you need to know about isosceles triangles is that their base angles, they are always congruent to one another. Now, what do I mean by base angles? These are the angles that are opposite the equal sides. So this angle would have to be the same measurement as this other base angle. These are the two base angles. Okay, that idea I think will also prove helpful for you on some of your practice problems here today. Okay, another thing I want to briefly look at here with you is the Pythagorean theorem. Okay, now it's important this only applies to right triangles. Okay, so you can see here's a picture of a right triangle. The legs are often referred to as a lowercase a and a lowercase b, and here we have the hypotenuse as c. Basically, the Pythagorean theorem is if you take one leg squared, add to that the other leg squared, that should equal the hypotenuse squared. A lot of times the Pythagorean theorem is seen as a squared plus b squared equals c squared. Very important that the c, though, is referring to the hypotenuse. Okay, and then I want to just take a look here with you at what are called similar triangles. Okay, now similar triangles does not necessarily mean that we're talking about triangles that are exactly the same. They're not congruent. They're two triangles where their corresponding angles are congruent. So they have angles that are the same, but then the corresponding sides are actually proportional. So I want to show you what I mean in this picture right here. Okay, so basically in this picture, now this doesn't have to be right triangles, even though these two pictures might look like they're right triangles. Okay, the angles like angle C would have to be congruent to angle Z. Angle A would be congruent to angle X, and angle B would be congruent to angle W. Well, clearly you can see, at least in this picture, if this is drawn to scale, that the side lengths are not congruent. So when we say the corresponding sides are proportional, here's what we mean when we talk about similar triangles. If you were to take side A, okay, it is proportional to side X, and side B is proportional to side Y. Same thing with C and Z. So you can create a proportion. A proportion is really just two fractions that are equal to each other. So you'll notice if I'm putting B in the top of this fraction, in the top of the other fraction, I would want to put its corresponding side, which is Y. I have A in the bottom of this fraction, then I would want to put in the bottom of the other fraction the corresponding side. So I'm going to create another set of proportions here from this triangle. Let's say that I put side C in the top of this fraction, then what I would need to stick over here would be the side that's proportional to that. That would need to be Z. If I were to put side B underneath here, then I would need to put Y there. Okay, that's how that works. Okay, last couple things we're going to look at here just to kind of review some basic geometry is that of circles. Okay, a couple formulas you want to make sure that you have committed to memory for the ACT regarding circles is the circumference formula. This measures the distance all the way around the outside edge of a circle. The circumference formula can be written either as pi times diameter, okay, or the circumference formula could be written as 2 pi r, okay, because if you double the radius, 2 of the radius equals the diameter. Okay, now you don't want to confuse that though with the formula for the area of a circle. Okay, the area of a circle is pi r squared. Okay, pi r squared. That then gives you what all of the area, the space is inside of the circle. Okay, and lastly, we will look at trapezoids here. Okay, trapezoid. Basically, what we're talking about with a trapezoid has one set of parallel sides. Okay, and those parallel sides are referred to as the bases. So you can see here in this first picture, these are my bases, but please make sure that the left and the right sides of your figure it does not have to be those could be the bases, in other words. Okay, it doesn't have to be the bottom or the top. So in this other picture here, the bases are actually the left and the right sides. Okay, whatever the parallel sides are, those are the bases. Okay, also one other thing worth noting is the height of the trapezoid is whatever the perpendicular distance is between the two bases. So for example, the height of this first trapezoid here, it's not these diagonal sides here. The height would be whatever this perpendicular distance is there, or in this case, the height would be the perpendicular distance connecting the two bases. Okay, here is the formula for finding the area of a trapezoid, something that also could prove helpful on the ACT. You're going to add the lengths of the two parallel sides together. Those are the two bases. You will multiply that by a half, and then that will get multiplied by the height, which is that perpendicular distance between the two bases. Okay, that is it for the review of basic geometry. At this point, you could stop this video or pause this video. I'm going to ask that you do the 11 basic geometry problems that are practice ACT problems here. It should be your practice set for basic geometry. It would be ideal if you could time yourself. Generally, it's about a minute a question, but if you gave yourself about 15 minutes to try those 11 problems, and if you needed to, then you could unpause this video, and I'm going to give a quick explanation of each of these 11 problems here. Okay, when you have finished doing those 11 problems, we'll go ahead and start here. I think the very first problem was a great example of you've got two parallel lines in this transversal T, and the question is, which of the following lists has three angles that are all equal to each other? So we're looking for three angles that are equal, and you can see we have 5 answer choices here. Okay, so we want to be thinking through some of those different angles that we reviewed when we did those little notes on basic geometry here. So I'm looking at the picture, and the one thing that I'm noticing, at least from these answer sets, is angle A is in 3 of the answers, B is in 2 of them. If I look at angle A and I'm trying to find any other angles that would be equal to angle A, I immediately would think, well, angle B should be equal to angle A because those are vertical angles. The only other angle that appears that would be equal to angle A would be angle D. A and D are corresponding angles. B and D are alternate interior angles. So I think the only answer choice for this would be letter A. Okay, letter A is the only option for that. Okay, let's jump down to number 2. Okay, here you can see that you are given, it mentions, I think there's a little bit more detail in the paper that you got. It gave you some more details here. It actually said that this was an isosceles triangle, I believe, and it referenced that AB was equal to side AC. So I'm going to add that to the picture here. Okay, and they give you that angle BAC is 40 degrees. And the question is, what is the measure of angle ACD? So we're looking for this measurement here. Now, what comes into play with this is knowing that if this is an isosceles triangle, then these two base angles have to be equal to each other. And we have to know that there's 180 degrees in every triangle. So I'm just going to call these angles X degrees, since I don't know what they are. If we were to add 40 degrees plus x degrees, that would be 40 plus 2x, and I know that has to total 180 degrees. If I solved this equation for x, I would get x to be 70. Now, I'm going to just caution you here. You really have to make sure that you are answering this question. There is a reason they put 70 degrees here as an option. Okay, look at what question this is asking. What is angle ACD? I'm looking for this angle out here. When I solve for x, that's actually telling me what this angle in here is. Okay, so when I fill in that I know that's 70, actually I'm looking for the supplementary angle to that 70-degree angle. I need to do 180 minus 70, and that's how I arrive at 110 degrees, letter C. Okay. All right, let's take a look at number 3 here. Okay, number 3 says, we have this diagram below. It shows a pasture which is fenced in. All but one section of the fence runs either straight north-south or east-west. Consecutive fence posts are 10 feet apart, except for the one diagonal section. Do you see the diagonal section here in this? The one diagonal section is right there. Everything else is either vertical or it is horizontal, and it mentions that those are 10 feet apart. Okay, so we know all of the lengths of each of these segments with the exception of the one diagonal segment that I highlighted. The question is, which of the following statements best describes P, the perimeter of the pasture? So we are looking for the distance all the way around the outside edge. Well, this whole left side, if you were to go through and add up 10, 20, 30, 40, 50, 60, 70, that whole side there is 70 feet. If I move across the top, it looks like this one is 30 feet. And if I were to go all the way from here to here, it looks like it'll be 10, 20, 30, 40. I'm just counting the horizontal segments only when I'm moving across this way and this way. Okay, now if we go vertically, now I know we got that diagonal segment. I'm going to ignore the diagonal piece for a second. We'd have 10, 20, 30, 40, 50, 60. I'm only counting up the vertical pieces, 60, plus the one diagonal segment. Okay. Now I'm just going to add up what I have right now. Okay. I know that the total, if we were to add up 70, 30, 60, and 40, that totals 200 feet, but I need to add the length of that one diagonal segment. Okay, so here I can look at these answers, and they do this to you a lot on the ACT. We should right now be able to eliminate some of these answers. Keep in mind, this is a time test. You want to try to move through these as quickly as you can. I know that my answer is definitely going to be bigger than 200. Okay, so at this point, I don't know, as far as eliminating some of these, we could probably eliminate some that don't feel like they make very much sense at all. But let's just take a closer look at this diagonal. If I were to make this into a triangle here, like a right triangle, and I'm going to draw a more zoomed in picture here, or zoom out rather of, well, I guess it would be zoomed in, of this triangle here. Okay, this vertical segment would be 10, and this horizontal segment would be 10, okay, because that matches this, and this matches what that length would be, okay. If we really wanted to know what this hypotenuse is, we could do the Pythagorean theorem, okay, one leg squared plus the other leg squared equals c squared or x squared, and if we work this out, we would be taking the square root of 200. Square root of 200 is roughly 14.14 units. Okay, so that means my total is 214.14 feet here. Okay, so the logical answer for this has to be letter A. Okay, all right, let's take a look at the next one here. Okay, a person has a rectangular shaped garden with sides of length 16 feet and 9 feet. The garden was changed into a square design with the same area. Okay, so we know that it started out 16 feet by 9 feet. If I multiply 16 and 9 together, the area of that rectangular garden is 144 square feet. Now they're going to change this so that it looks more like a square, but it says it's going to have the same area. So I know the area still needs to be 144 square feet. Okay, how many feet in length are each of the sides of the new square shape? Well, if it's a square, the two sides have to be congruent or equal to each other. So x squared would equal 144. If we take the square root of that, that means the sides would each have to be 12 feet. Okay, let's take a look at number 5. Okay, number 5, in this figure below, we have a right triangle. They give us these different side lengths, and the question is, what is the length of side AC? This is just a Pythagorean theorem problem. Okay, I'll just call that missing side here. We'll call it side B. Make sure that you're putting the hypotenuse gets squared by itself on the other side. Okay, if we were to work through this here, now here's where you'll notice these answers are not in decimals. Okay, so one option is you could, if you type in the square root of 27, you're going to get a decimal. Okay, and then you're going to look over here at these answers, and none of these are in decimals. You could type these in and compare the decimals to this. Okay, or this has this written, if you were to break 27 down into its prime numbers, okay, and every pair of identical factors you can cross off. Square root of 3 and square root of 3 is technically the square root of 9, which turns into a 3, so we pull a 3 out in front. This is the same thing as 5.20, which would match letter B. Okay, but if you think it's faster, you could just type these into your calculator and compare the decimal with 5.20. Okay, all right, let's take a look at number 6. Here we're talking about the central angle of a circle is 30 degrees. It says it's subtended by a circular arc of length 6 meters. So we're saying the length of this arc right here is 6 meters. Okay, how many meters in length is the radius of the circle? Okay, well, few things we could kind of think through here. We know that there's 360 degrees in every circle. So if we were to go all the way around, there's 360 degrees. And we're really just talking about this one little slice of this pie, this part of this crust right here, this arc length is 6 meters. And that comes from just a 30-degree angle. So we're curious to see, well, how many sets of 30-degree angles could we get from a full circle? Well, you could get 12 arcs that were just like this one. Okay, there's 12 arcs if we were to go around and chunk this into 30-degree segments. Okay, well, let's look at our circumference formula. Okay, the circumference formula can either be pi d or you could view it as 2 pi r, either way. Okay, so we're looking for the radius. That's what the question is. What is the length of the radius? We want to know that. Okay, so if we were to say, well, if we can get 12 of these arcs, and they're 6 meters each, that means the circumference is going to be 72 meters. So if I plug 72 into this formula, and you can use whichever version of these two formulas you want, okay, it doesn't matter which one here, okay, I'm going to go ahead and solve this for the radius. So I'm going to divide both sides by 2 pi. And then it looks like we can reduce 72 divided by 2. That reduces to 36, but I still have the pi symbol in the denominator. You can see that matches with letter D. Okay. All right, here we have a rectangular box. It has a base of 2 inches by 6 inches and by 10 inches tall, and it holds 12 ounces of breakfast cereal. Okay, so now let's just be clear, and this is the old box. Okay, this is talking about a rectangular box, because we're just going to be talking about a new box here in a moment. Okay, so 2 times 6 times 10, it technically is like 120 cubic inches, but they're saying they're only going to fill 12 ounces of cereal in this. Okay, now the manufacturer, he wants to use a new box. Okay, so he wants to do a new box, and he wants the base to be 3 and the width to be 5, but we don't know what the height is for this new box. And then it wants to have the exact same volume. Okay, we want the exact same volume. So that means it's going to have 120 cubic inches of volume in it. So if we made an equation, and maybe right here in this spot here, I would put maybe just like an x. So we'll say this is 15x equals 120. I'm getting 15 from multiplying these together. If we solve this for x, we would get x to be 8. Okay, so the height of that box should be 8 inches if it's supposed to have the exact same volume. Okay, so this, like holding 12 ounces of breakfast cereal, this is almost like extra information that isn't really needed in order to do this problem. Okay, let's look at number 8. Here we've got a circle inside of a circle. It says in the figure below, the circle centered at B, that's a smaller circle, is internally tangent to the circle centered at A. Okay, when it says tangent, it means it's just touching the edge of the circle just at 1.1 right there. Okay, the smaller circle passes through the center of the larger circle, and the length of AB is 5 units. That's labeled here in the picture, okay, AB. So you can see the radius of the small circle is 5 units. If the smaller circle is cut out of the larger circle, how much of the area in square units of the larger circle would remain? Okay, so here's what we know. The radius of the larger circle would be 10 inches. So really, the diameter of the small circle is the radius of the large circle. Okay, I'm going to say radius of larger circle is 10 units. Okay, now remember, our area formula for circles is pi r squared. Okay, so if we were to take the area of the large circle, again, the radius is 10, the area of the large circle would be 100 pi. Okay, but that actually includes the area of the small circle. So now we need to subtract the area of the small circle from that. So if I were to plug in, I guess here, the radius of the small circle is 5, so it'd be pi times 5 squared, or 25 pi. And now we're going to take 100 pi minus 25 pi, and that leaves you with 75 pi. Okay, you need the pi symbol on that. That gives you the answer C. Okay, all right, last page. Last 3 problems here. You want to kind of time these up. On average, this should take roughly, a minute, minute and a half per problem. So you're moving through these pretty quickly. Of course, I'm explaining these. It's taking a little bit longer to explain these. Look, here we got a trapezoid. It says in this figure below, we've got AB and CD that are parallel. So I'm going to kind of show that here with these little arrows. Okay, the lengths are given. In units, what is the area in square units of the trapezoid? Okay, remember, the formula is to take 1/2 times base 1 plus base 2, multiply that times the height. Once again, the bases are the 2 parallel sides. All right, well, I can see from this picture that the height is definitely 4. That has to be the perpendicular distance connecting the 2 bases. I also can see that the top base here is 10. I'm needing to find this bottom base. Well, if I cut this down here as well, I know this is 10, but I'm needing to know these other 2 sides here. And so to get this missing leg on this right triangle, because that's actually what this would be, I would need to do the Pythagorean theorem. Okay, so off to the side, I'm going to do my x squared plus be 4 squared. That should equal the hypotenuse 5 squared. If you're familiar with this, this is a 3, 4, 5 triangle, by the way. If you knew that, you wouldn't have to mess with what I'm doing here right now. This other leg is going to end up being 3. Okay, so if this leg is 3, that means this leg over here is 3. So then that means this whole base down here is going to be 16. Okay, if you plug that in, you get 52 units squared as the area of that trapezoid. All right, let's take a look at a problem that maybe involves some similar triangles here. We have a 6-foot spruce tree. It's planted 15 feet from a lighted street light. Okay, so here's the street light. The lamp is 18 feet above the ground. So all of these numbers here I think are already labeled here. Okay, how many feet long is the shadow? So the shadow is where this question mark is. Now, I think what's tricky about this is when you're setting up proportions, okay, 2 fractions that are equal, you need to make sure that the numbers you plug in for numerators and denominators need to be complete sides of triangles. Okay, so I'm just going to redraw these 2 triangles. I've got one bigger triangle here. This is the street lamp. I actually don't know the entire bottom length of this big triangle. I know that it's 18 plus, I'm going to call the shadow of the tree X. Okay, then the smaller triangle made by the tree, which I know is 6 feet, the bottom of that smaller triangle here would be X. Okay, now I have my sides, so I think we can plug in. If I do 18 here, I'd want to do 6 there. Those are proportional sides, and then 18 plus x there over x there. Okay, now to solve this, you can just cross multiply. So we'll take 18 times x. We're going to set that equal to, you want to be a little careful here, you'll need to put this in parentheses so that you can distribute. Okay, and we're just going to gather all of the x's on one side, solve for x. Remember, x in the picture represents the length of that shadow. Okay, it'd be 7.5 feet. Okay, And our very last problem, in this figure below, we have the lengths DE, EF, and FG. They're all given and labeled. And the question is, what is the area in square units of triangle DEG? Now I'm going to highlight that. That's this triangle here. Okay, remember the area formula for a triangle is base times height divided by 2, or maybe you write it like this, 1/2 the base times the height. Okay. Now the base in this triangle would be 12. Okay. The height is the perpendicular distance from this top vertex extended down to what would be the extension of the base. So the 10 here is actually the height. Sometimes we call that the altitude of a triangle. Okay, if you multiply this together, you get 60 square units. That would be option C. Okay. Hopefully you didn't do too bad when you tried these, and hopefully some of this stuff will prove as really great review for you. Here were the answers, and these are kind of the various topics that each of those 11 problems were through. All right.